Yeah, anything you like. Go ahead. Actually, it might make it easier for you if I go like that, and you can see all the slides, and you can find your favorite slide and see which one you want to ask a question about.
Can I ask a question?
Sure, please.
Go ahead.
First of all, thank you very much for the talk. This is Martin Wegener from Karlsruhe speaking. To the last part of your talk, these perfect band gaps, as you have called them, is there a fundamental limit how large you can make this band gap relative to its center frequency?
Well, I suspect there is, but how would you prove it? I mean, we tried as much as we could, for example, by varying as much as we could, but I mean, the best we could do was with the Meta rod, and even with the Meta rod. Has anybody ever I would like to ask a counter question. Has anybody ever been able to prove mathematically anything to do with maximum band gaps in anything? Because it sounds like a very difficult question to me. Because you have to consider all possible geometries. How are you going to consider the whole space of possible geometries to even answer this question? It sounds like a mathematics question.
Yeah, I do not have a sound answer to my own question, but in optics, if you look at photonic band gaps, the gap tends to be larger if you crank up the contrast in refractive index. You already got a lot of contrast here, right? I mean, basically the voids compared to the aluminum or whatever it was. So that's what brought me to this question.
That's exactly right. And I don't know in optics if you ever can make a structure. Well, you could make an identical type of structure where you have vacuum, but the difference in optics is, well, I don't know how high you can get your refractive index, but you're going to get light that's leaking into the vacuum in optics. But here there's no sound essentially leaking anywhere. So you could put this in a vacuum or you could put it in air and it's not going to change anything. So whether that's a good thing or a bad thing, perhaps it's a bad thing because it gives you less. You would want to put water around it and see what would happen, for example. I don't know. There are so many variables you can change. So I would think it's very difficult to prove that you've got the best possible.
Yeah, thank you anyway.
Good question. I really would be interested to know because, as I said, we had to start using the idea. We've even started doing that now, but tapers does work. But it's not really the point, is it? You are thinking about a unit cell which is not diatomic. It's a monotonic unit cell, I presume, your question. Is that?
Yes.
Because if you make a diatomic unit cell, probably that could include two unit cells which are slightly different size. So it's that's kind of cheating, isn't it?
Well, if you call that a supercell, I wouldn't call it cheating.
Okay, if you're allowed supercells, then you have 10 different sized cells connected together, and then you repeat that. Then you're going to get a wider band gap. And I think that's the way to go.
But then the answer would basically be that you can make it as wide as you wish. The band gap.
I presume so. Depends how you define it. If you want to, there's always going to be a cutoff at the lower frequency. So yes, you can define it as the gap frequency divided by the gap mid frequency. Yes. So I guess you could go on indefinitely increasing it, presumably. But I think the big problem with my application is to do it at a low frequency. Everyone in acoustics wants to succeed below 100 hertz or below 200 hertz. And then everything gets difficult because the materials become difficult and probably you're just going to end up with a rubber damper being the best thing. But I was just hoping it might be possible with this approach.
Yeah, actually, that was the first thing I was thinking about. In many optical tables, you have an issue with resonances in the range of 10 hertz or so. And it would be fantastic if somebody could get rid of these frequencies and I was exactly doing the same scaling as you did, but the foot for the optical table would be ridiculously big.
I see. Okay. I see. Thank you for the question.
Hi, Oliver.
Hello.
I was just a slight side comment. There's some work in electromagnetism on the bandwidth of absorbers that uses the theory of analytic functions, like the Kramers-Kronig relations, and you can get bandwidth results that are independent of how you actually make the absorber, what the composition, whether it's a metamaterial or whatever. I just thought there might be something there.
Well, I guess my dispersion relation is incomplete because I should show real and imaginary parts. And
yes, I see.
So that's the next thing to do if you want to do this properly.
Yeah. Mm-hmm.
And
I had a question.
Yeah. Well. Okay. Fair enough. Go ahead.
Mm-hmm. I had another question as well, which is when you showed the extraordinary transmission through the small rod. You didn't show anything about the shear waves. What happens to the shear waves?
The shear waves are visible if you plot, say, the x component of the displacement or the y component of the displacement. There are shear waves. They travel at roughly half the speed of the longitudinal waves. But we didn't want to go to the trouble of finding them, measuring trying to determine their intensity. We'd have had to determine the acoustic Poynting vector for that. And it would have been a lot of trouble. So there was already one study on shear waves by the group of Johan Christiansen. And so I refer you to his APL. And well, since it had been done, I suppose we wanted to concentrate on the longitudinal waves. Actually, we didn't even know it had been done when we wrote the paper, but we found out later. Yeah.
Okay, thanks.
It would be interesting, yes. And the shear waves are what's probably giving the damping, well, the extra damping that we saw.
Okay, right.
Yeah, the study is incomplete without the shear waves, so it needs to be done.
Mm-hmm. Okay, thanks.
Anyway, don't be fooled by the efficiency. Efficiency is just one way to classify the phenomenon. And even if you have a high efficiency of 500, doesn't mean you have a high transmission. So it's not going to be it's not like the solid rod. It's not going to work as well necessarily as the membrane in the pipe, which really had almost 100% transmission. Notice I didn't talk about the transmission at all of the rod, because you'd have had to put it in a waveguide for that. That would have been a different study. I hope somebody does that.
Sorry. Did you look at extraordinary transmission when you have a large bandwidth?
Sorry?
Extraordinary transmission over a large bandwidth.
Yeah. Are we talking about what slide do you think that would be?
I mean, any slide you had on the acoustic extraordinary transmission, could you come up with a solution?
Do you mean in air or in a solid?
For instance, in air. Yeah, let's keep it simple. Yeah.
Yeah. So what is the question?
In fact, you have ways also to get extraordinary transmission over a very large bandwidth.
How would you do it with a large bandwidth, you mean?
Well, it's actually initiating some kind of, plasmonic behavior. Then, in fact, what happens is that as soon as you reach this kind of plasmonic behavior, your wavelength could be extremely large. You will still get extraordinary transmission. You can get extraordinary transmission over an extremely large bandwidth.
It's absolutely right. What you're saying is absolutely right. If you decrease the size of the hole, it gets better and better in acoustics. Have you ever seen a microphone? How it works? A microphone is covered with a mesh, like a chicken wire, like a fishing net, but made of metal. And nobody never worries how a microphone manages to transmit the sound, even if it's made of metal, and the size of the pores in that mesh are only very tiny. But it turns out if you do the acoustic theory of transmission through a tiny hole, it gets to 100%. So you don't need to put this membrane in if you make the hole small enough. But as I showed you, for this size of hole, which is still not small enough, then you still can benefit from.
Yes.
Then you can still benefit from putting the membrane. And in this respect, the acoustic problem is totally different from the optical problem, which never has this wonderful, suddenly good transmission when the hole becomes tiny. Yeah. So that's maybe what you were saying, partly.
Yeah, because in fact, even in optics, some people came up with metasurfaces. They call this gold plasmonic checkerboards, and they managed to get 100, or well, at least 80% of transmission throughout an extremely large bandwidth with, similar actually properties.
Actually,
to this. Yeah.
Good point. I mean, I have got a slide ready to answer this question. I actually have a slide on it. So this is, where is it? This one? No. Yeah, it's up here somewhere. So let's have a look where it would be. This one. Yeah. So this is the analytical formula for the resonance width of extraordinary transmission through a hole with a membrane stretched across it. You see it's the mass of the membrane plus the air around it times the resonant frequency divided by twice the impedance of air times the waveguide area squared. If you want to keep your frequency the same, okay, you're focusing on a single frequency of interest. How do you make a wider bandwidth? By reducing the mass. So how do you reduce the mass? You can't just make a lighter membrane, because I said the air makes up most of the mass because it's shifting this air. So you have to make a lower mass. Easy, by making a smaller hole. And if you make the hole small enough, the Q factor becomes very small, which means you get a very wide band and very nice transmission. Yeah. This is the equation. This equation is written in our appendix of our, it's not written in this form, but if you just look at the appendix of the paper we wrote, there's a formula for the Q factor. And if you take the limit of no damping and stuff like that, you get this equation.
Okay.
Yeah.
But effectively, here you focus your interest on, a very high efficiency. And the efficiency, although you would have a high transmission, would be very low. So effectively, I was very interested I never realized that the efficiency of Ebesen's design was so low, because its transmission is so high. I never actually...
what did you say was so low? What is so low?
In fact, if you have a very broad band, so what would be the efficiency of your design, in terms of the efficiency you designed earlier?
Oh, okay. The efficiency in the case of very broadband.
Yeah. So do you mean that the efficiency would be very low? That would be the price to pay?
The efficiency, I think, gets better and better. There is no theoretical upper limit for the efficiency. I'd like to say that straight away. There is no theoretical upper limit. It can be anything. If you consider the size of atoms, it's different, but I'm talking in continuum acoustics. So there isn't a limit to the upper limit. So efficiency should increase as the hole size goes down. And I'm not so proud of our 500. Okay, in solids, it's a very high efficiency, but you can still do better than that.
But
so I don't think efficiency is a very good measure, actually. It helps you write a paper and get it accepted, but I think the actual absolute transmission is a better guide. Yeah.
So in fact, Ebesen was really not concerned with efficiency. In the end, it was really after only the transmission properties, isn't it?
That's true. There are some papers where it's not even mentioned, the efficiency, but usually they say how much more light gets through than it would be if it.
And actually, I would like to mention in 1981, the group of Ross McPherson together with Daniel Mestre, they published a paper on extraordinary transmission. It was an experimental paper, which is hardly cited by Ebesen and other people. And I could send you this paper because it's a very nice story. It was published in 1981 in I3 Transactional Magnetics. And this was done in an anechoic chamber, and just after the experiment, the anechoic chamber burned. There was a fire, and all their experimental facility was burnt. But they could publish this paper, which was published 2 decades before Ebesen.
Sounds interesting.
Yeah, very interesting. So
it's a kind of extraordinary transmission paper.
Totally. It's just like microwaves, but it's extraordinary transmission.
They wrote the paper. It was just not noticed. But I mentioned one that from 1974, but I didn't know about the one from 1981.
Yeah, and I did not know about Ulrich, but I know very well about the one of 1981 that Ross McPherson keep publicizing, but for some reason people don't pick it up, and it's a fantastic paper because there is a theory of gratings by Daniel Mestre, Michel Navier, and there is experiments which were made by Professor Deleuil, and there is also Ross McPherson as a co-author. Very, very nice paper, hardly any citation, and just the same stuff.
Of course, before the word acoustic metamaterial existed, lots of people published papers on local resonances, so you can argue a lot of phenomena were discovered well before you thought they were.
Well, surface placement polarity is just theory of gratings. It's the 1970s, these things are already known. No? It's spoof placements. You can already find it in the book of Roger Petit, 1991, again, Springer Verlag, yellow book, but people keep rediscovering this and making it, perhaps. Anyway, so very nice. That was a historical point.
Yeah, sorry about the hiccup in the middle, but yeah.
Anyone else has some questions regarding even potential outreach activities with what has been shown? Because obviously your macro cell, yes? Please?
Yes, I have a question, especially about the metal bar, which gave you the perfect band gap. It looks you try to optimize the structure, but with the constraint of being in plane of the bar. Can you do a little bit better if you allow, for example, to go out of plane with some of the parts?
No, we did out of plane. There are this one is out of plane.
Yes,
and
but all
this one is out of plane.
Yes, but the components are flat, almost like you try very hard.
Oh, I see what you mean. Out of plane design.
Yes.
Yeah. Okay. Yeah, that could be done. Yeah. I mean, you could attach 4 of these metabars to make a square, hollow thing. I don't know how they would interact, but maybe they wouldn't interact all that much because you can see the edge of the material here is very rigid. So if you made 4 of them into a square, you could make a sturdy coffee table leg, which I haven't thought about before. I've just thought about it now, but it's a nice question. Thank you for that great question. Yeah.
So I asked the question because usually if you want to place a few modes at the same frequency, you will use symmetry principles. And clearly you are very limited when you are in plane with this symmetry principle. But if you are allowed, for example, to use 3D shapes, then you have more options.
And this would be better designed by an algorithm, not by human iterative labor. So if you stuck an algorithm to repeat this, of course, you need quite a lot of techniques, because one of these runs to determine the dispersion relation maybe takes a few hours on COMSOL. So I think it might take a long time to do but on a supercomputer, yes, it would be good to optimize like that.
There was also discussion about the limit on the gap. I would like to mention that there is an upper limit on the decay of the modes once you create a gap, and there is an absolute limit which you can read entirely from spectral information, and 1 over the penetration depth, for example, goes as gap divided by the square root of the width. And in fact, it's gap divided by 4 square root of the width if you will be talking about Laplace operators. So you scale everything down to just Laplace. And you cannot beat that limit at all.
I guess not. I wasn't aware of that. Sounds interesting.
And that tells a little bit, even if you, so if you want to work at lower frequency, then there is a problem right there, because then the width becomes small, the width of the band below the gap. So then the penetration depth becomes larger. So it's a it's a tough problem.
I see. This reminds me of a paper by the group from Hong Kong, University of Science and Technology, where they calculate the minimum thickness of a wall for attenuating a given frequency of sound from an analysis in complex analysis, where they actually determine that you can't go any thinner than this if you want to do this to get this spec. So it's similar to what you're saying.
Yes, I know about that. I understood that was an upper bound, or which was known, for example, but was never published everywhere. But it was known for long.
Oh, really? See, yeah, there was some Russian paper on that, I think, a long time ago. Yeah.
Anyway, thank you very much for the talk.
Welcome.
Okay, so do we have any more questions, even from our applied mathematician friends? By the way, I have added the link to the paper in the chat box. So it's from 1980, the paper, not even 1981. Regarding your torsional modes, these are very difficult to measure, isn't it?
Which modes?
The torsional modes.
That's not too bad. I mean, you take the difference in you take 3-axis accelerations here. So subtract if you just look for the difference here, then you get them at both ends. You have them at both ends, the front end and the back end. So it's not so difficult.
And
what we would like to do, and what we might do, is use a heterodyne imaging system, so we have full information along the whole length of the rod at any frequency. So we can image the acoustic field, and then you have a lot more information. That's actually possible. So would be quite a nice thing to do.
And what is their propagation speed with respect to shear waves?
Now you're asking difficult questions because, okay, in this rod, you see, you can get it from simulations from the slope of you can get it from the dispersion relation, and it's, I can't remember the exact values, but it's 2,000 to 6,000 meters per second regime. So you look at the dispersion relation and you can figure out any velocities you want. I think you're asking about the meta. Are you asking about the meta beam in particular or the meta rod?
Yes.
The meta beam. This one.
Yeah. Yes, this one. Yeah.
Well, can't remember exactly what we said about the exact, I mean, in our paper. Yeah. Well, we probably said something about the amplitude of the sound velocity, I believe. I'm just trying to see what we said in terms of values. And well, we did also, okay, sound velocity. I think it's a bit difficult because you would have to say, do you mean the sound velocity at the limit of low frequency, or do you mean the sound velocity? Which sound velocity? I mean, in the case of the meta rod, it's a bit easier to answer that question. But here, all I know is what the density and longitudinal sound velocity are in the bulk. Of course, I know that. That's 6,000 meters per second. For longitudinal waves in aluminium, which is what it's made of. But if you want any sound velocity, you're going to have to look on this graph here, and presumably a very low. I mean, it's not even a bulk, so it's a waveguide mode. So I don't really know the answer. We didn't calculate them, but you could figure them out if you calculate them from this graph. You can see the highest sound velocity is compressional, next is torsional, then shear horizontal, then shear vertical.
It's very, very close to shear.
So I could, if I had a calculator, I could tell you, but it's from this graph.
Some people in Los Alamos, they've made an experiment, so it's in a block of rock, and they have some rods on top, and they have measured the propagation of torsional waves on this, kind of in between Rayleigh and torsional waves. It's quite fun.
This is another, what shall I say, criticism or another negative point about our study is that we didn't show the mode shape that corresponds to this dispersion relation. So we could have chosen some points on this dispersion relation and showed the shape of the mode going down the rod. That would have been interesting. But then it would have been in a very long paper. But yes,
kind of,
that it would be interesting.
This kind of surface torsional modes are extremely interesting in terms of their polarization and so on. When you look at the polarization, it's very specific.
Why do you call it a surface torsional mode? Because why?
Well, because in our case, actually, it was a substrate, but you have the kind of plate version. But you find the similar stuff in a substrate when you put elements on top. And this is really reminiscent. It's very interesting to see these torsional modes. Very, very nice. So you say essentially that from your graph, their velocity is almost the same as the shear. It is very close. It is very close towards the lower part of the spectrum.
These two here?
Yeah. T and SH.
Yeah, they're very close.
Oh, it's the same frequency. Same
T
wave
is in the
speed.
wrong place in this
Yeah.
graph. Yeah.
It's almost the same.
The T should be here, sorry. Yeah, this is the T.
Yeah. So effectively, they are very close. And of course, the pressure longitudinal is much faster. So you would have first longitudinal, and then you would see the torsional, and then just soon after you would see the shear, the SH, and then
Yeah, you have a pulse. Yeah, that would be.
of course. This is what I mean. Yes. Okay. In terms, arrival time. The first one you would see is first the longitudinal and then the torsional. The second one you would see arriving is the torsional. This is what you say in this paper, essentially.
Yeah. Actually, we did. We did make a movie of the waves going down the meta rod.
Yeah.
I can show you that.
Oh, wow.
Somewhere I have that. That looks maybe a little bit more convincing, perhaps. Here. Yeah. This one. So this may be of interest. Can you see the screen now?
Oh, yeah.
Yes.
You can see this?
Oh, yeah, this is very good.
I should have shown you this. My mistake. Okay, so...
it's lovely. The torsional mode is really lovely. The animation for the torsional mode is beautiful.
Yeah, I suppose it is beautiful, yeah. AB means two frequencies. Well, A is out of the gap and B is in the gap.
Okay.
Actually, this is not the same design. This doesn't have the little rod at the top here.
Plus here, wait a minute. Yeah. So here it looks like a torsion is the fastest. It has
this one. Yeah, in this one, the torsion is the fastest. But
Oh,
this
wow,
is
you
not
can
the same.
actually-
This
yeah.
is a different design.
Yeah,
You can
oh,
see
very
the unit
interesting.
cell here. This is the unit cell.
But then it's quite amazing because here the wave speed of the torsion and the longitudinal wave is nearly the same.
Yeah, that's
You
true.
see? Wow, so you can really tune the speed of the torsion with your design. Oh,
Yeah,
wow.
well, this design just removes the, like I showed for the coffee table leg, we removed the top rod. That's all. And also, we don't have this star shape. This is a solid block. The other one was deliberately made to be able to slide something into a tube, and yeah, it was a bit easier to do it that way, and you only have to glue at 3 points. But if you make this one, I don't know how you make this because it's got, yeah, we did try to make it. We just made the unit cells by gluing and stuck them all together, but it's difficult to make this. Perhaps 3D printer could make this quite easily though. I'm not sure. Yeah, there is a lot of different designs you can do. As you see though, this one doesn't have such a nice wide band gap. The other one I showed you is 20%. This one is about 10%. So we favored the one with the biggest band gap, which is here. Yeah, as you know. Yeah, you can see it, the star-shaped thing at the end there. Yeah.
Can I ask a question? So when you kick the bar, it made this pristine sound. What frequency was it? And
that's 1 kilohertz. But I'm pretty sure that's 1 kilohertz, but I'm pretty sure I excite harmonics.
It's a higher harmonic, you say?
I think this is a kilohertz. But there's so many harmonics, I can't tell which is 1 kilohertz.
And set in even if you hold it from any point. It doesn't matter if you hold it by hand.
I'm sure you should be careful with. You should be careful with that. There you go. There's a nice 1 kilohertz probably. It depends where I bang it and in which direction. So if I excite the longitudinal mode as much as I can, then I don't know if the Zoom is allowing you to hear it or not, but
yeah, we can
that's more or
hear.
less, maybe that is, actually there's a lower frequency there, which probably the whole bar is resonating. So it's a bit difficult to get to the 1 kilohertz out of that mess. Yeah, a lot of mess. But I'm sure it depends on where I hold it in terms of the longitudinal modes of the whole bar, which is confusing the issue a little bit. Yeah. So that's why when we measured the ratio of the amplitude at one end to the other end, we saw interference resonances off the band gap, because off the band gap, the thing is just a multiple reflector, and some frequencies are going to build up and some frequencies are going to cancel out. So there are a lot of these little dips and interference dips. But that doesn't matter, because in the band gap, nothing gets through, and then you just see nothing at the other end. So it's not trying to measure transmission in an infinite bar, which would be more in line with some analytic or some theory, but it's just to show where the gap is that we were trying to do. Yeah.
Yeah, it seems.
I'm
It's
interested to
interesting.
know what other designs there could be for this.
Yeah, because usually the musical instruments, you would like to have a linear dispersion, but here you have such a strong dispersion, especially around 1 kilohertz. So it will be a very
yeah, that's right. This I don't think I have a. I should mention that we're going to try to make. I don't know if any of you are nano people, but we're going to try to make this bar of a dimension of microns and then see if it works on the nanoscale. It's not really very much different, the physics, but imagine if you were a future civilization who could make any structure with atoms at any precision with, like 3 atoms thick here and 1 atom thick there. You might be able to make a metal rod that's thermally insulating, over a wide band. And then you could use some metal rods to thermally insulate something on the nanoscale. That's the sort of thing you can put into the introduction of a paper to a journal with start with a capital N or S or something, maybe.
So I guess.
Who knows if you could make some wire that doesn't conduct phonons because it has such a wide band of a wide band gap that heat won't even go down it. You could make a thermal insulator out of something that's actually a thermal conductor. That would be interesting.
Yeah, well, so perhaps when you go to those scales, you'll try to make it out of glass, of silicon wafers, something like that?
Yeah, we're thinking of silicon nanomachining to make. The problem is we don't have so many choices of exciting all the modes and testing one by one, because it's difficult, this experiment. You have to do torsion, in-plane shear, out-of-plane shear, longitudinal, and each time you have to glue the piezos in a different place, and it's not an easy experiment in that respect. I mean, it's not that difficult, but it's a little bit laborious. And on the nanoscale, if you want to excite a torsional mode, it's a bit tricky. I don't know how you do that.
Yeah, you have to load it through waveguide sideways somehow.
Yeah, you could do off-center excitation or something. Just change the symmetry of the excitation. Yeah, maybe. Probe at 2 points or something.
The thing about thermal insulation, when you try to insulate the house, phonons play a very little role. What you have to, it's the the circulation of the air, that's what's the worst, and not the vibration. So so if you have air flowing around, then this structure will make very little impact on thermal insulation.
Maybe.
Unless you are in a vacuum or something like that.
Could we go back to outreach activities? You know, you have this macroscopic unit cell. So how could you, use this, for instance, in in a museum or going to schools to explain metamaterials? What would you do,
Which particular part of this talk you mean?
It's, when you have this mass, instead the large cell with the springs, and you have the inertia that makes. So, for instance, if I'm thinking of outreach activities in schools, so, what would really make the fun,
Okay, I know the answer to this question, maybe.
If I would be interested, for instance, to disseminate this, let's say, in secondary schools, how can I,
Okay.
I quite like your device, but something which would be easy to make and quite.
Okay, we are working on a. Well, I tried a long time ago to do. To do something that would filter the sound, So you put it over your head, and you talk through it, and if it has an acoustic band gap, then you can sing a scale like do, re, mi, fa, sol, la, ti, do, but it doesn't sound like that to the kids. All they hear is do, re, mi, fa, la, ti, do, and they don't hear the sol because you design your helmet to cut out that frequency. So that's what we're trying to do now, but so far we didn't quite make it. The trouble is the ear is logarithmic, so you have to make it really good damping at the frequency of interest. But we're nearly there. Unfortunately, it's rather heavy, so it's not like a very light helmet. It's a very heavy thing that goes over your head. But it's a long story, actually, about that. And I don't know if I have, I really don't know if I have a picture, but we tried to make one with a phononic crystal a long time ago. And I don't remember if I still have the picture of it or not, but
because this is very heavy. This is really something that we would like to do in this association. It's also, to have outreach activities. We really want to reach out to kids, not just to researchers, to kids, secondary school, even primary school. How can we, make them enjoy physics with funny stuff from the world of metamaterials, but easy to design,
Is something I'm also interested in. And well, in acoustics, think you can get a dragon wash bowl. Have you heard of the dragon wash bowl?
No.
Okay, I have a dragon wash bowl here.
Oh, okay.
I have a picture of the dragon wash bowl here. Where is it? Yeah. Bit difficult to look at this. Okay, this is getting in the way. Okay, I can't get the. Okay. So. Yeah, okay. So this shows, I mean, it's related to wine glass vibrations. But it's fun for kids. For example, picture of the flamingo at the zoo. the flamingo at the zoo will, can you see them vibrating their beak like
Yeah.
that
Yeah.
and making ripples coming out like that?
Hmm. Ah, yeah. Okay.
So
Like
this
always
kind of
the
this kind of single
interference.
frequency, single
Uh-huh,
free, single frequency excitation of water waves from a point source can be found in a natural. Flamingos have this oscillation of their beak, which is monochromatic in acoustics. Yeah, and that is just to show you what a water wave is, but you can exploit water waves in the Dragon Wash Bowl,
Oh, wow.
which is like a wine glass mode, but in a very large pan.
Oh, wow. Oh,
So
fantastic. Wow.
this is the Emperor Hongwu
Yeah.
from China from a long time ago, 1328 to 1398.
Wow.
And he wanted to get his son to wash his hands,
Yeah.
wash his face in the morning. And so he bought him a Dragon Wash bowl, which is known since 3,000 years ago, in fact. And he got him a Dragon Wash bowl. And then, as you know, it's like a wine glass. So diagonally, there's a antinode. So you get 4 nodes. He's pointing the 4 nodes. And then, then there's 4 antinodes here. So
this one is
that's
really
a nice,
fantastic.
that's a nice thing for kids because it splashes, you know.
Yeah,
It
yeah,
splashes very well. And the other thing that's nice for kids is,
yeah.
well, what else is nice for kids?
You can't beat the Dragon Wash Ball.
Can I say that?
I saw this device I saw this experiment in
Wow.
one conference somewhere in
What else?
Wales.
Lovely.
And yeah, it's
you can
equivalent
change
to what you could.
It's an amazing device.
But you can
can
change
see it
the
on a wine glass.
geometry of the surface to visualize more modes, I'll say.
Okay. If you are very, and yeah, the wine glass mode is like that, and that's the same as the Dragon Wash bowl, yeah. So that's nice. And then you can them a hydrocrystallophone, which is well-known way of getting a wine glass noise to continue by having a rotating spindle and lots of different diameter rings. So this thing sounds very funny. This is Mozart.
Wonderful. So, I've seen this one before, actually.
And this one is another, this one is, stop that. This one is another one. So it sounds horrible like that. But this one is, yeah.
Lovely.
Anyway, this one is, somebody said in this newspaper article that it was very depressing listening to the hydrocrystallophone, but I think it's fun, yeah. Yeah, this sort of thing is good for kids anyway, I think, yeah. So what else is good for kids?
Actually, maybe we might get in touch with you, because if we want, to have these kinds of outreach activities, and if there is a way for us to try again to have this event in London in 2021, we might wish to have you as a public speaker, but with this kind of stuff. You see, this is what we would like to have, because to welcome not university students, but kids,
I'm quite often, I have something even more crazy, actually. I mean, better than anything I've told you so far. If you're interested, just quick, very, very quick, okay? Where is it now? Where is it? Yeah. So there is an incredibly interesting acoustic phenomenon, which, which is I refer to as mysterious Maya melodies.
Okay.
So this is an interesting phenomenon. That's this sound.
No.
Now this is the sound of this bird.
Uh-huh.
It's called the Quetzal bird, and it lives in Mexico. Okay, so this is Mexico, okay? And it's, okay, this is Merida here. And Quetzal bird looks like this.
Wow.
And it has this characteristic voice. Very sweet bird, very rare bird. Okay, the feathers are very prized. The feathers were prized by the Incas. And the Incas built these pyramids. There's one here in Chichen Itza, in Yucatan, in Mexico. And the bird is singing like that. Pew, pew, pew. And so in this Chichen Itza place, looks a bit like this. And I believe you know what happens on top of a pyramid, but that's not, that isn't the story today. So I was there.
Oh, wow. Okay.
I was there for the Photoacoustics conference in 2000 and whatever it was,
Wow,
10 years ago.
lovely.
And
Lovely.
you can, I'm going to clap my hands in front of this pyramid.
Okay.
So you see the sound of the echo from the pyramid sounds the same as the voice of the Quetzal bird. And why would that be? Okay, well, these guys also want to hear the Quetzal bird.
Oh, okay. Yeah.
Everybody likes the noise of the echoes. Okay, it's very simple to explain because the echo that comes back to you first has a period determined by the lateral step size. But the echo that comes to you later has a period determined by the diagonal step size, so a lower frequency. So it starts high and it ends low. So it's pew, pew, pew. That's the sound of the echo, okay? So they said the mystical god Chak, the sound of the people walking up and down the pyramid sounds like the mystical god of water, like a waterfall. And they also, okay, jaguars are a feature. Yeah, I'm just telling, I can't show you now, but I have an instrument from this part of Mexico where you blow it and it sounds like the jaguars cry.
Okay.
And I want to just finish by saying this is my favorite bird, but it's nothing to do with South America. So I think you might know this bird. Okay. So I think you know this bird. Maybe.
Bonjour, Bogdan. Well, Emile, come on.
So this is a very funny bird. And probably you know it's the kookaburra, okay, from Australia. But I like this bird. So, yeah, that's another acoustic phenomenon which is nice for kids, I think. Wouldn't you say so?
I think it would make really a wonderful lecture, you know, if you could, you know, be there. Of course, I mean, we can't have this virtual. You need to be there in person, you know, but if we can have this conference, we could have, for instance, kids from, you know, the Lycée Charles de Gaulle and from other, you know, schools around, and perhaps also some kids coming from East London, not only, you know, these rich kids.
Mm-hmm.
And
Yeah, it sounds nice.
And maybe, you know, some of them, they would love this and become future physicists.
That
You know, and that would
be
be a
good.
great job done.
That is the objective, I guess. Yeah,
Yeah.
definitely.
So we have already, last year we had, Mark Olderyd, who was lined up to give a talk on bats, bioacoustics. We have Martin Wegner giving a talk on invisibility and all this kind of stuff. And you could really also give a talk, you know, on this kind of, well, great acoustical phenomena. And I think, you know, a whole afternoon of this kind of stuff, then we have like, I don't know, 100 kids coming with their teachers. And then they can even have some project, small project on it, you know, following the talks and so on. And
Nice.
we want to promote this also in the association. We want to promote science, you know.
Is this in France?
It's in London. It's in London.
London.
Is it not in France?
No. We want to do this in London. The association
Oh,
is
in England. Okay, that's good. No problem. Either way. Yeah.
If you're very keen, you know, we can also envision that then you can have a stop in France. And I mean, I'm sure that, for instance, I can run something in Marseille. If you are really keen, I can.
Could be. Yeah. Sounds great.
Yeah, that's something.
Anyway, yeah, lots of fun stuff for kids in acoustics, definitely.
Yes. This kind of stuff anyway is great. And your Dragon Ball wash, I find it amazing.
If the age of the kids is not like, if they're high, like over 15 or over 13, they don't mind just listening to like that. But if they're younger, like 8 or 7, it's best if you give them something like to touch by themselves. Yeah. Like make a musical instrument by themselves or something like that.
And I've seen that on your website you have this kind of lamp, you know, you sell some light. Can you tell us a little bit more on this?
This one here?
Yes, this activity. Can you just say in a few words?
Yeah, well, that's waveguide physics for you. Yeah. This is a waveguide light. So this is based on the light coming from the base, inside the base. And there's quite a bit of different physics in this light, actually. But the light's inside this base. About 21 different LEDs, 21 LEDs in this base. Okay, this waveguide is made of acrylic and it's 4 millimeters thick. And it's got very, very finely polished edges. So it's kind of, there are several optical phenomena here. There's total internal reflection of the light, of course, and it comes around the bend. And then the edge of this light has two edges, like 2 faces here. You can't see very well, but the light is divided into 2 beams, major beams, and overlap to produce a uniform illumination on the desk.
It's lovely.
So it's kind of very comfortable to work with. And because this edge is so flat, I don't know if you see the stripes, but there are some stripe effect here. And that's from multiple reflection between the faces. So that's an interesting effect. And so you've got refraction, total internal reflection, and multiple reflection, all in the same device. And this one is made of wood. This one is wooden, but there's also aluminium ones. And yeah, this one's on sale in Europe at the moment, actually. So
you've got a website?
It's a bit expensive. Hi, sorry?
You've got a website. How much is it?
This one is on sale.
We are interested.
Okay, yeah. This light starts at 290 euro. 290 at the moment. It's expensive. And this one is a wooden one, so it's more like 430. So it's pretty expensive.
It's good wood.
And
this
light is another one. But this one is not on sale in... Sorry, got you. This
Yeah.
one is not on sale in Europe.
Okay.
This one is only available in Japan at the moment.
Wow.
This is a waveguide light again. Then, so you have LEDs in the base,
Yeah.
and the light comes up this tube, and it comes round like in this flower-shaped, and then you can put, this ball is just to stop the dust getting in, but this is actually a crystal.
Okay.
This is actually glass crystal. So this goes here. And this one is called, what's this one called? Yeah, this one is called Glow Wide.
Okay.
And this one is called Fontana. And
Okay.
so, yeah, where is it? Where is it available? Yeah, that's a good question. But I mean, this one,
Really lovely, yeah. This,
I mean, it's quite interesting to compare the different colors available. And yeah, for example, yep. I don't know if you can see this, but can you see this?
yeah.
Yes?
Wow. I know that's amazing. That's amazing.
This is the company name, Plum Science.
Okay.
In England, plum means good. You see, like plum job or plum position or
Okay.
plum, yeah, what? Plum post. So
Lovely.
plum could be good science. Plum science could be good science. And glow wide means, you know, glowing very wide because it illuminates a wide area. And so, you know, it's useful on your desk like that. You can have a white one. And okay, this is what I showed you, but this is actually a simulation of the wave coming out, the ray optics for different illumination angles at the base. So because it's a double edge here, you have a lot of rays that are spread out. And actually we did deposit a patent on this. To get more uniform, you can optimize this shape, the angle of the two faces, and also the size of the two faces. Can you see the waves are gathering on the outside of the curve? That means one of the faces should be slightly different size from the other one to give the best angle. It's a bit complicated, but with multiple iteration, you can get the best shape. It's based on Helmholtz coil physics because two magnetic fields will overlap to produce a more uniform magnetic field. Two coils will produce a more uniform magnetic field than one. So two beams coming out the tip here gives a more uniform field than one. So then you've got this infinity mirror, which is this stripy shape on the outside. And that comes from the image of this edge being projected in many different representations through multiple reflection on this edge. So you see stripes. So that's another, it's like a Hall of Mirror effect, like a zebra. And the other interesting thing is no shadow. So because it's a wide beam, if you hold a pen up,
very important actually.
Yeah, you hold a pen up there you don't get a shadow because light's coming from lots of different angles. So that's a nice kind of sales point.
Yeah.
And the area you get illuminated is 60 centimeter by 40 centimeter.
Quite wide.
So it's quite nice. And okay, there's a few things like not much power used, 6 watts. Good LEDs from Japan, 6,000 hours. It means it lasts as long as you do. You know, it can last 20, 40 years. Nothing goes wrong. And you get...
That's good. That's excellent. Bogdan, we might even think, you know, of buying some for the association. Wow, that's great.
It's amazing.
It's amazing. It's totally amazing, this stuff.
And I had a chance to play with this device, the ball, and it's amazing. And you see all the particles going on in all the direction, exciting. And
you know, Oliver, if you want, what we do is charity, it's not commercial, but we can certainly give the link to this company if this is related to what you do in science. Because this is, it's great.
I'm not sure that we didn't lost Oliver again.
So that's the end of the session then. I mean, it's absolutely stunning, this device. It's the price is high, but it's super. It's super nice. Anyway, I just wanted to mention that we are trying very hard with Bogdan and Richard to find a date for 2021. Huh? We really want this to happen this time, this conference. So we really have to work on this, Bogdan. Huh? As soon as we have more info on COVID, we should try to decide upon a date.